Now in this example, I will build a simulation model for a 2 degrees of freedom system, the system shown right here. Now in this system we have two variables, x1 and x2. So it's going to be a little bit different, but we will start with the same approach that we change the equations of motion so that the acceleration terms are on one side and the rest of the terms are on the other side. And we start again with introducing the variables, defining the state variables using a system of integrators. So I will insert integrator number 1 and then number 2. And these two integrators for the variable x1. Here we have the acceleration dd x1 double dot, and on this right here we have dx1, the velocity of x1 or x1 dot, and finally the output of the second integrator is the variable x1. Now I'll do the same for x2. We'll just copy these two integrators. Get a little space here. Okay. Now x2, here's the x2 acceleration, ddx2, and dx2 for x2 dot, and finally x2. Now let's start with x1. We have the sum of two quantities, x1 and x2. x1 is negative, x2 is positive, and the sum is multiplied by a gain. So let me start by introducing the gain. A gain right here, which is going to be 2 divided by 3 m1, and then another gain over here, which is going to be, the gain for x2 is 1 over m2. Now for x1 double dot, it's the sum of two quantities, one positive, one negative, so I will introduce a sum block right here, and another sum block for x2. For the first block, it's a positive and then negative input, so I will change this to a negative sign. Now the negative signal is x1, so I will go from here to x1, and the positive is x2, so I'm gonna go from here to x2 right here. Now x1 is multiplied by k1 plus k2, so I'm gonna need a gain here. Here's a gain block inserted in x1. All right, and x2 is multiplied by k2, so this one was k1 plus k2, another gain k2, This is K. Okay, so now the input to ddx1 or x1 double dot is 2 over 3 m1 multiplied by k2 x2 minus k1 plus k2 times x1, which is basically this equation. And x2 double dot, again, we have a positive and a negative input. So I'll change the sign right here to plus minus. Now, the positive term comes from x1, so I will connect this port, this positive port, to x1. And the negative port to x2, right here. Now, x1 is multiplied by k2, so I will add again right here. Let's make some space. Okay, and this gain is again k2. Now notice something. I hit k2, I get an error signal because there's another block called k2. So what I'm going to do is to go around this, I will enter space k2. It's not going to show up, but it will change the name for MATLAB, so it doesn't see that the two blocks have the same name. Again, we have k2 multiplied by x2, so I'll copy this right here, and the name is changed to k1, so I will change it back to k2. And for conflict, I will add 2 spaces so that MATLAB accepts. Now, here we have now the complete system. I want to add the scope to see the output. So here's the scope. Okay. One input is from x1, and the second input is x2. Right click and take it to the scope. Okay, here we go. Now, let's run the simulation. Here, open the scope. First, before we do that, let me use these values, these parameters. 2 kilograms for M1, which makes this 2 divided by 6, and M2 is 1 kilogram, so this is 1 divided by 1, that's okay. K1 plus K2 is 250. K2 is 50, and another 50 for K2 right here, and finally 50 right here. Now to the scope and hit play, and nothing happens because we don't have any external input or with initial conditions. So what I'm going to do is, let's put an initial condition on x2. Let's assume that we pulled the mass m2 downwards, let's say a distance of 0.25. So I'll go to the integrator right here and insert an initial condition 0.25 and see how that affects the whole system. Okay, here we go. Here we have the responses for x1 and x2. Let me go to modeling and reduce the time step Solver details, the maximum step size, let's set it to 001, and rerun the simulation so that the lines are smoother. And here we have the two outputs. We have harmonic response. We cannot see pure sine wave here. We have sort of mixed waves, and that's obviously because we have 2 degrees of freedom, so the system has 2 frequencies, so the response will be in the 2 frequencies, omega 1 and omega 2, and these signals are basically a mix of frequencies, so that's why you see a mix here. You cannot distinguish the 2 frequencies just by inspecting the output right here. You have to run an FFT, fast Fourier transformation, fast Fourier transform function on the outputs to determine the frequency content. That's another topic. But as we see here, we have a continuously harmonic response because we don't have any damping in the system. Finally, I can again reduce the system to one block by creating a subsystem. Okay, and now for this subsystem, all the equations of motion are in here. Now if I want to add external initial conditions to the system without having to go into the system every time, so what I will do here, I will go inside here. First, let me rename the outputs here. For out1, I will call it x1, and out2, I'll call it x2. Now the initial condition here is x1 0, so let me make it external, and another initial condition for x1 dot, let me set it to external. Okay, and initial condition for x2 external, and finally an initial condition for x2 dot external. Now how can I have inputs introduced to a subsystem? We don't have any input ports, but I can insert input ports from the library. We go to the ports and subsystems, and here we have in. This is an input port. Okay, so I will have this for x1 not, and another one, copy, paste for x1 or dx1 0. Paste, and this is for x2 0, and finally for x2 or dx2 0 for x2 dot. Now if you go out to the main page, you will notice that we have now 4 input ports to the system. Let me connect x1 0 goes here, x1 dot 0 over here, x2 0 right here, and x dot 0 2 goes right here. Now go up one level. Now to introduce initial conditions, I will use simply source constant block. So here's a constant. I will call it x1 not. Another constant for dx1 0. Here we have to have a 1, and then also copy these two blocks for the other two initial conditions. This will be x2 0, and this is dx2 0. Now, to connect these blocks to the subsystem here, let's call it the drum mass system. I can either draw lines from each port to the corresponding port right here, or there's a shortcut. You can select all blocks here, press Control button and hold, and then click on the target block, and the lines will be automatically connected in the same sequence. Make sure that the blocks here are arranged in the same sequence as the ports on the subsystem. Now, if I set the initial conditions all to 0 except for x1, x1 was 0.25. That was the option we used first time. And going back to the simulation here, run, and we have the same response. Now I can play with all the initial conditions right here. I can change this to 0 and see what happens if I introduce an initial velocity on the drum, say 1, and let's see what happens. We have another form of the response. The frequencies do not change. If you compare this output to the previous output, you will notice that we have the same frequency content, except that the amplitudes have changed from one simulation to another. So this is how you simulate a 2 degrees of freedom system using Simulink.